Okay, so what we saw yesterday was the idea that you can use KK transform to validate data. There are integral equations which relate the real and imaginary parts. If you have the entire spectrum, you can use this to validate. But if you want to use the integrals, you do need to have data in a wide range of frequencies. That ideally from 0 to infinity. In practice, you need from very low to very high. Okay. What's meant by very low to very high? Very low meaning it should settle at some level that will be considered low. Settle meaning if I have data at high frequency, I have data point, increase the frequency, it still stays somewhere there. I bring to low frequencies, it comes like this. Out this location, if I decrease it further, it still stays around here. This is one example. Okay. Instead of this, I may have another example where it comes like this, but after this it remains there. That means it has settled there. Then I can call this as wide enough frequency range. What if I do not have data that goes to low frequencies? I have data coming like this, it comes here, and then at low frequencies it is noisy. So, I know it is not good. So, I would delete this data and say I am not able to get clear data below this, but within this limited range I have good data. It may or may not be possible to use the integration method to check when you have data in a limited range. You can use extrapolation, but sometimes it will work, sometimes it will not work. Okay. We also saw one example where KKT can be used to detect instability, where experimentally a potential change was superimposed deliberately to make it unstable. So, I want to continue with one or two more examples and then go to another type of problem that you would face. Normally, we use impedance data. We get impedance data from the equipment and we use impedance data to test, but sometimes you will have to use admittance form. So, I want to show where you have to use admittance form and what are the ways to tackle that situation. And when we realize that we have a problem that frequency is not wide enough, frequency range is not wide enough, how do we handle that situation? Okay. You have to use another approach, it is called measurement model approach. You can use your own software to handle that. You can also use a free software called Linear KKT, which uses a measurement model approach with certain type of constraint. So, I want to show those examples also. So, we will continue first where we left. So, in this example, this is a numerical simulation. We start impedance measurement and the potential initially drifts rapidly and then it settles down. That means, in the first hour it goes from 0 to 100 millivolts less, and then it is more or less the same. Given by this equation, I have given minus 100 millivolts, 1 e power minus bt, the b will tell whether it will go down rapidly or whether it will go down slowly. If you take the spectrum or if you simulate the spectrum, you would get it like a semicircle, that is what you would expect if it is stable, but it has a tail. And sure enough, when you try it with the KK transform, you would see that at low frequencies there is a clear difference between what is transformed and what is original. This does not tell you what would happen if you do not have instability. It just tells you that the system has a problem. Of course, this is synthesized data. I have simulated this data. So, I can go to whatever frequency I want. Low frequency means I can choose and get millihertz, microhertz without much of problem. I also want to show you a couple of cases where you have large amplitude perturbation. That means, you are applying a sine wave, but the sine wave amplitude is very large. And if I look at a DC potential versus DC current, or I should say DC current versus potential, and I have drawn this in log scale, it goes from microamps per centimeter square to 10 milliamp per centimeter square. In log scale, it is not linear, it is non-linear. In this example, if I take a spectrum at one of the DC potentials here, I can use a small amplitude or I can use a large amplitude. Nobody would use 300 millivolts, but this is just to show what would happen, and this is done in simulations. Okay. I get two different spectrum. Looking at this, you can easily say, yeah, this is 1 millivolt, this is 300 millivolt, that means nonlinear effect is present. If I get 1 millivolt and 2 millivolt spectrum, it will be identical, it will overlap. When I go to very large amplitude, it is clearly different. So, I can say this nonlinear effect is present, and I have not shown it here. If I take 1 millivolt data, and take the blue color line as simulated data and do KKT, they will overlap. If I take 300 millivolt data, we show that it does not overlap, there is a difference, which basically means KKT tells us that there is some problem with the AA spectrum. It does not tell whether it is instability, whether it is large amplitude, whether it is causality, but it tells you there is a problem. But this is one example. I want to show another example. Okay. This is actually experimental data. This is taken by Professor McDonald's group. 5 millivolt data is the black square here, and larger amplitude 100 millivolt data is green round. Look at this, you can say definitely these two are different, they are not same, which means this has nonlinear effect. However, if you do the transform, you will find that they more or less overlap for the 100 millivolt data. 1 millivolt data also will show they overlap, which means you cannot rely on KKT to always detect the problem. Remember, we looked at the conditions and said it is not necessary insufficient. That is, if it is linear, causal and stable, it will definitely be KKT compliant. If it is non-linear, it may or may not be KKT compliant. That means, in this case it is non-linear, but this is still KKT compliant. But as of now, this is the best we can do. We can apply KKT and check whether it has a problem or not. If it has a problem, you will have to think about what is wrong in the system and how to get stable results or how to get results at linear regime. If it is fine, if the transform data matches with this, then we hope that everything is fine, and mostly everything will be fine, okay, meaning you will be in the linear regime by and large, but there is no guarantee. That is what is given by this example, that if it matches well, because we know that data is acquired at 100 millivolts and we know that 5 millivolt data looks different, we can say yes, this nonlinear effect is not captured by this KKT. But in general, if all that you get is this data, the best you can do is to transform it and check if it works well or not, and most of the time you will find the problem. So, that is something that you should do first. This is another example. Okay. This is simulation result where the Z real 0 is here and the positive values are on the right side, negative values are on the left side, and the impedance spectrum starts here at the high frequency, goes here, shows a loop and comes down and settles here. You can see there are more points here, it is denser. So, it settles at this value. Right now, do not worry about the origin of the spectrum, just believe that this spectrum is quite possible in real system, and I can show you examples where we have got data which look like this. Later we will see what is meant by this negative resistance, why do we get a data like this. Right now, let us say somebody gives us this data, okay. We transform this and you can see at the high frequencies the red and black lines overlap. At the low frequencies they are clearly different, and in fact they look like mirror images. This is a data simulated, synthesized by us, and we have ensured that there is no instability and there is no nonlinearity in this. So, we expect this to be KKT compliant, but when we use the integral, it does not show that it is compliant. So, we have a question, is the data wrong? Data is good. Is the software doing something wrong? I do not think so. What happens is impedance is not the right form to feed this software under these conditions. We have to take admittance, admittance is 1 by Z, okay, and feed the admittance to that. That means the KKT equations which we used to write as ZRE, on the right side you have integral, you have ZRE and Z imaginary, you would have this in the imaginary side and you would have this on the real. This we have to replace with YRE and YIM, and of course, on the right side you will have to have it as a function of imaginary and real. So, if you use it as admittance, it will transform correctly. Out here high frequency, the impedance is close to 0, because it is simulated data. If you have a solution with solution resistance, high frequency data will not be 0, it will have some finite value. And when I use 0 and when I try to calculate the admittance, it becomes very large number. It will become infinity if it is exactly 0. If it is close to 0, it will become large number, and when we do the calculation in MATLAB, there are round of errors. So, in order to avoid that, I have taken original data and added 100 ohms to that. That means the impedance that I get here will not be 0, but it will be close to 100, which means when I take the admittance, the number will be more accurate, that is all. This addition of 100 ohms is to make sure that I am not in the region of round of error in the MATLAB or any other software that I am using. And then I calculate the admittance, transform it, and when I transform, I see that the transform data and the original data match well. Now, I have to tell you why should we use impedance, why should we use admittance. In one condition we use impedance, one condition we use admittance. Okay. If the system is stable under potential static control, sometimes called potential regulation, what we measure is current, what we control is potential, and the function that transfers the potential to current is admittance. Under galvanized static control, we measure potential oscillations, we apply sinusoidal current, we get the potential and we do FFT on it, whatever analysis we do, and based on that we calculate the impedance. So, the transfer function for potential static EAS acquisition is admittance, the transfer function for galvanized static EAS measurement is impedance. If the system works well under both conditions, potential static as well as galvanized static, then you can use either admittance or impedance, and in both cases KKT will show you that it matches well as long as it is linear causal stable. If the data is acquired under potential static control, the right method or right feed to the program is admittance. Many times it so happens that the system would be stable under both galvanized static and potential static condition. Sometimes, as an example here, the system is stable only under potential static condition, it is not stable under galvanized static condition. Right now you have to trust me, but later I will show you example where you would get this spectrum, and I will also describe how you would get this spectrum, and I would also tell you that it is not stable under galvanized static mode, and you will be able to follow why it is not stable under galvanized static mode. Right now you have to trust that this system from which we have acquired this data, that is stable only under potential static mode. In general, if you see the impedance going to the left side here with negative values for impedance, real part of the impedance, that will be stable only under potential static condition, which means you will have to use admittance form. That is one way. You can employ one or two tricks to use this in impedance form. See, by and large when you use a software, commercial software, and get the data, what you do is to say these are the settings, give me the impedance from this frequency to this frequency. You can say constant potential, you can say constant current, depending on what facilities are available in the instrument, you will get the data. And by and large you will get only impedance format. You can convert it to admittance format yourself, but you will get only in impedance format. And the natural tendency is to use that format to check. If the data comes on the right side of this, it is fine. It would be stable under potential static as well as galvanized static. So, you can use impedance as it is, and that is what I have done before. In the previous examples, I have not used admittance, I have given only in impedance form. Although using it in the admittance form is correct way, using it in the impedance form works fine because those systems happen to be stable under galvanized static condition. I can use a trick. I have this data and I will call this as ZF or Z system, Zs. Now, if I add a resistance in parallel to this, because the units are ohm centimeter square, I am going to say 50 ohm centimeter square. What would happen is I can get impedance of the total system here, and that would come to the right side. I will have to choose this carefully. Why do I choose 50 ohm? Because I see here that it shows some value close to minus 120, 130, etc. So, if this is large value in the magnitude, do not worry about the sign here, and this is small value of impedance, current will go through the smaller one. When this is small, it will go through this value. So, I have to choose a value which is less than the value here. When I add this 50 ohms added in parallel to the data, I get a spectrum which comes completely to the right side. So, the idea is this: I want to know whether this data is KKT compliant. Here of course, it is smooth, right. When you get experimental data, it may not be like this. I can either move it to the admittance form, I have to do it with care so that I do not get into round off errors and do the transformation, or I can bring it to the impedance form. It is already in the impedance form, I can bring it to the impedance form where the data is on the right side of the plane, and if this system is KKT compliant, I know this is a simple resistor. So, if this entire system is KKT compliant, that means this is also KKT compliant. If this system is not KKT compliant, problem must be coming only from this, because this again is simple resistor. So, what I have done is to move it to the right side by adding a resistor in parallel. This data has moved to the right side. If you look here, low impedance, that is high frequency data, it effectively has low impedance. This 50 ohm is 50 ohm regardless of the frequency, ohm or ohm centimeter square, right. Here this is a variable, at high frequency it is a low value, at low frequencies it has a large magnitude. So, what would happen when I go to high frequencies? This may be like 2 ohms, then the net impedance of this system will be close to 2 ohms, little less than 2 ohms, but close to 2 ohms. So, at high frequencies data is more or less the same as original data. When I come to middle frequencies, it is moved a little bit. When I come to low frequencies, this is minus 100, this is plus 50. You can say most of the current will go through this, some of the current will go through this. Okay. It is negative, of course I have to explain what is meant by negative resistance. Right now just say that we can do the calculation and get the value. Later I think I can convince you that negative resistance has some meaning, and this is what it means, it is not physically unreasonable. Now, what I mean by this is I bring the impedance values to the right side of the plane, that means in the complex plane plot the Z real which forms the x axis or abscissa, all the data is on the right side of the y axis, all the data has positive value for Z real. In this case this data can be transformed in the impedance form itself, which is what normally you can use commercial software for KKT validation. Some of the software at least come with this choice. I want to show you an example. Okay, this is of course some dummy data. Okay. This is one example. Depending on what software you have, you may have different many choices there. In this, if you go to the menu saying extrapolate, and for whatever reason they have given it as calculate impedance, it would show you the transform data and the original data. The green color is the calculated value, red color is the original value, and you can give it in different formats: Bode plot, real and imaginary, in the normal Nyquist or complex plane plot. However, here if you take a data that goes to the negative side, you can't ask it to do the transform in the admittance form, and they do not even tell you how they do this. They just do the transform by some method and give you the result. And for whatever reason, if you say Kramer-Kronig routine, that does not do the KK transform here, that does an extrapolation using KKT, extrapolation to lower frequencies. So, if you want to check for KKT, you should use calculate impedance in this system. Likewise, other software depending on whichever commercial software you are using will have some way of doing the KKT. But I think by and large they expect that you have the data in the correct format, which in their feed it is going to be only in the impedance format. However, when you have a problem with the result, we want to know, okay, we do not have impedance data in the wide range of frequencies, and extrapolation will work sometimes, it may not work sometimes. Now, you have a data, you transform it, it transforms well, you are happy. It does not transform well, you have questions. Is it because the data is not KKT compliant, because it is violated one or more of the constraints? As an example here it does not transform well, and it is because it is unstable. Is it because the frequency range is limited? Another example which we saw before, it actually comes from a clean system, but we cut the data or truncated the data, and then when we transform it does not match well. Here we know what we are doing, but in general you get a data, you hope you have done the experiment correctly and you got the data, or somebody has sent you the data, you hope that they have done it correctly. Is the system unstable? Have they used large amplitude? Have they saved the data by mistake? They saved some wrong information, we do not know that. And if it is truncated, you can't really do much about that, meaning I can't extrapolate it reliably all the times. So there is another way to handle this. This idea is proposed by Professor Mark Orizum from University of Florida. The idea is this: we have some data, I want to get a system which I know is KKT compatible and see if I can generate the same data. If this data which we got, whatever form it is in, okay, if that can be reproduced by another system which is known to be KKT compatible, then I can say this data has come from some system which is KKT compliant. Now, if I take impedance from a system which contains resistance, capacitance and inductance, they are called passive elements. All the spectrum that comes from them will be KKT compliant. So, in such cases, let us say you have an RC system, RC meaning resistor and capacitor, which looks like this, and we know in the complex plane plot, if I take data, it is going to look like a semicircle from high frequency to low frequency. If I take data at many frequencies, this is how it will look like. This is minus Z imaginary, this is Z real. But let us say I have taken data only up to this. So, I have partial data, still I know the system is good, system is KKT compliant, and this I can model using this circuit, and I know the circuit is KKT compliant. So, this approach is called measurement model approach. So, we say if you can model the experimental data using a circuit which contains only passive elements, then this data is KKT compliant. Okay. We model it well, model it adequately, we have to tell what is meant by that. Now, if we cannot model the data, if I try modeling it and it does not fit well, I have two choices. One, data set is not KKT compliant, another, maybe I am not doing it correctly in terms of modeling. Okay. So, if I take this data, of course, this data most of the software will model correctly, but if I take some other set of data and I come up with a circuit that I think will model this data well, and I know the circuit is KKT compliant, I am not modeling it correctly, meaning they are not matching, maybe I did not do it correctly. If I use different choice of circuit, I might get this correctly. If I use different initial values for the guesses, I might model it well. So, that doubt is always there, and we will see how to overcome them, how to ensure that we have done our best in terms of modeling. Then if it does not match well, you can say data has some problem. Now, I have to tell you how to implement this method. It is one thing to say, yeah, you take this circuit and then it has to model it well, then we say it is KKT compliant, but how do you go about implementing it, and what do you mean by adequately model it or model it well? So, I want to show you type of circuits that can be used for this. One, you have a resistance which can be thought of as a solution resistance, and you have one capacitor and resistor in parallel. This type of circuit is called Voigt circuit. You can add more number of them and keep increasing that number 1, 2, 3, 4 n. This type of modeling is with Voigt circuits. Another type is to use a capacitor and resistor in parallel for the simplest circuit, and when we want to add more and more elements, we will call this is second Maxwell element, Maxwell pair, this is third Maxwell pair, and so on. We can keep increasing the number. And by the way, these are equivalent, meaning from Voigt circuit I can move to Maxwell circuit and back. Third possibility is to use what is called ladder circuit, where you have the solution resistance. This typically it will be used to model a capacitor, AA capacitor. Simplest case, I will not have C2 or 2 etc., I will just have C1 R1, and that is the same. So, the simplest circuit of resistor, capacitor and another resistor, you can think of it as a Voigt circuit, you can think of it as the simplest Maxwell, you can think of that as a simplest ladder. The moment I add one more RC, depending on where I add it, if I add it here, I would call this as the second level Voigt. If I add it here, I will call it as a Maxwell, and if I say I am going to add it here, I will call it as a ladder. And just like capacitance, I can add an inductor, that is also okay. If any of these circuits with any n model the data well, okay, we can say the data is KKT compliant. You can use inductor if you want, if it is necessary. Now, the thing is, if I can model the data with 10 Maxwell pairs, it does not mean I know what is happening in the system and each of these element has some physical significance. All that we want to do here is to say this data has come and this KKT compliant system can produce this data. That is all that we are checking here. We are not trying to find what is the meaning of R1 value being 100 ohms, or what is the meaning of C2 being 20 microfarad, what is the meaning of C1 being 10 millifarad, none of these things. We just want to see whether data can come from a system that is KKT compliant. So, if you have to model this with 10 elements, it does not mean when you go for physical interpretation of the data, you have to go for 10 elements. It just says that the data is KKT compliant or not. So, that I want you to remember. First time when we do the data validation, you can use any of these circuits, check it, if it comes through clean. Next, when you go for actual modeling, you will have to think what is the system, how do I think it can be represented, and then model as per that idea. Now, when we model, when I say it models well, what do I mean? When you model this, you will get a simulated data, you have the actual data. The difference we call it as residual. For each data point, you will get a residual. Okay. In fact, one data point is a complex number, it has real and imaginary part. You can get the residual as real part, this is the residual, imaginary part, this is the residual, and plot it as a function of frequency. It is an example. One way to define a residual is to say exp here is the experimental. So, I will take the real part, experimental minus model, divide by the absolute value of the complex number given in the model, that is one way. I can use this and say I will not normalize it, I will just use the residual as it is. I can say this, instead of saying absolute value here, I will use z real experimental as a normalization or z real model as a normalization factor. This is all fine. You have to be careful that you are not going to a value which is very, very small. At the high frequency, do not use a very small value for the denominator. If it is close to 0, it is going to disproportionately push this up. So, at high frequency, you may see the residual is very high. You have to check, is it because my impedance is very close to 0, I am having this problem, or is it because genuinely the model and the experimental points are different. So, this is one form of definition. You can have your own definitions, as long as they are meaningful, it is okay. Now, if the residual values are small and they are randomly distributed, then you can say this data is by and large modeled correctly. If the residual values are large and they show systematic distribution, meaning they are not randomly distributed, then you know that model is not capturing the data correctly and there is a clean difference. Just verify that you are modeling it to the best of your abilities, and then if it still does not match, system has a problem, it is not KKT compliant. So, this is one example. So, we have 1 millivolt data and 300 millivolt data here. 1 millivolt data, I have fitted this to void circuit which goes like this, and I have denoted this as 2 white elements. If I fit this data to one white element, I will not be able to fit it, only one semicircle will fit. This RC can capture one time constant, this RC can capture another time constant which is given by this loop. So, 2 semicircles I can easily capture using 2 white elements. Residuals are pretty much 0 given by the blue color rounds here, circles here. The way I have defined the residuals is real minus real model, measurement model, divided by the real of the experimental value, and I have made sure that at this level it has not come close to 0. So, residuals look very, very low. This is simulated data, so I do not really have a standard deviation here. If I have experimental data, I should take few sets of repeats and then say at these frequencies, these are the standard deviation and these are the average values for impedance. Here I have used 1% of impedance and said that 1% of the impedance value gives us the confidence interval. So, if the residuals are very low and they are well within the confidence interval, I can say this data is clean data, 1 millivolt data That means if I fit this to 2 white element circuit and I do it correctly, I get no significant amount of residuals. So, this data probably arises from a KKT compliant system. I want to calculate the confidence interval. Normally, I will run experimental repeat runs, and when I calculate the confidence interval, what do I do? Do I take the average and standard deviation of impedance, real and imaginary values? Do I take the average and standard deviation of magnitude and phase? Should I do it for admittance, real and imaginary, or magnitude and phase? All of this will give you a different value, by the way. Okay. If I have value, just take simple real numbers x1, x2, and I take the average, I will write it as x1 plus x2 by 2. If I take the inverse, and I write this, I will get a different x average, of course divide by 2, correct. Do you understand? You will not get the same number by and large. If you are lucky, you might get same number or close to the same number. Standard deviation again will be different. What one should do is to find in which format the data acquired. If you apply potential sinusoidal waves and get data in the current, if you do it in pseudo potentiostatic mode, what you are getting is admittance, and if it is done with FFT, what you get is magnitude and phase. If it is done using lock-in amplifier or cross correlation, what you get is usually real and imaginary. However, what we end up doing most of the time is to use the impedance anyway. That what we see in the software, we click and get impedance, and we usually plot it. Of course, we plot it in all formats, but commonly used format is the Nyquist plot, where you plot real and imaginary values. So, this is what we end up using, or most of the people end up using, but if you want to do it correctly, strictly speaking, you should use it in the format in which data was acquired. Now, I have taken the 300 millivolt data and then I subjected this to model fit. I used 2 white elements. Blue circles show that they are not random, they are not small, and they are well beyond the confidence interval. And right now, trust me when I say if you use 3 or more elements, you will not get any better, which means I can tell this data is not KKT compliant. I can't use it now, but in this case, of course, I know I will have to reduce the amplitude and get a better data. Residuals are large and they show a non-random distribution. Now, can I keep increasing the number of elements? And there is always a question or a statement saying I can fit any data. If you give me enough number of elements, I will fit any data. You allow me resistance, capacitance and inductance, Maxwell ladder or any of this, I think I can fit any data. Meaning, you are using 2 elements to fit this circuit, but if you use 10 elements, I will definitely fit it. Maybe you are not doing it correctly. If you take the residuals and calculate the sum square, okay, sometimes it is called RSS, residual sum square. For 1 millivolt data, 1 element does not fit well, 2 elements fits very well, and after that there is no change. For 300 millivolt data, in fact, the residuals are little less at 1 element and then they decrease a little, they remain the same. This is for one type of definition. Even if you use another definition of residual, the value will change, but you can check for yourself that you will not be able to fit it better by going with more number of elements. So, it is not true that you can fit anything, you will not be able to fit anything, but you will get better confidence if you actually try this. Now, another question, are there cases where spectrum is actually good, but the model says I am not able to fit, therefore, it is not KKT compliant. So, its data is falsely flagged as, to the extent we know it is not possible. Even if you use elements called constant phase elements or Warburg impedance, which normally are not fitted with RC circuits, I have not discussed them yet, so we will discuss them later. Even if I get other elements which are not normally modeled using RC, if you put enough number of RCs, if the data is KKT compliant, you will find that the system will capture it. That means you are not likely to get false information saying the data is not compliant, and of course, it is up to us to make sure that the fit is the best possible. And later when we go to electrical circuit fit, I will also describe how to choose the initial values. If that does not fit well in the first attempt, can you do something to make it fit better. this software is given by Professor Baukam in University of Twente. It is called linear KKT. It is a variant of the measurement model approach. It makes it easy for us to apply this approach, measurement model approach, and check. So, when you ask, do I have to keep putting more and more elements? Do you want me to first model with one RC, next with another RC, one more, and then calculate the residuals and do all these things? Do I really have to do this, or is there any other easy method to do? Okay. I will describe that to you tomorrow. Okay. So, I wrote to Professor Baukam and to Professor McDonald, got permission from them to give the software to you. When you use it, you will get a better handle on how to take a real data and apply the KKT on this. Okay. When I show you here, you will get some idea, but you will forget it quickly. If you use it, you are likely to remember it for a longer time. Okay, we will stop here today.